So I'm Cameron Hummels. I'm a postdoc at University of Arizona. I've listed some of my collaborators on this project and some of the other projects I'm going to talk about here, and talking about mostly the circumgalactic medium. So investigating the circumgalactic medium is crucial for understanding a variety of topics that we've been discussing over the week. Things like galaxy evolution, galactic gas accretion, supernovae feedback, AGN feedback, all of these things tie back into the circumgalactic medium, which can be used as a probe, a direct probe, I'll argue, for a variety of these things. And really, the CGM, you know, we understand a lot about it from observations, but it operates in this unique space because it's the interface between the tenuous IGM and the star-forming ISM, and so you have a lot of different mechanisms going on there. You have stars forming and dumping, depositing metals, energy, and such into the CGM, and then you also have cold filaments and primordial gas flowing into and shocking in this region. So there's a lot going on. Observations have been in the last 10 years have really taken off, especially with the cosmic origin spectrograph aboard HST, enabling a variety of different observational studies like the COS halos to exist and to really touch on the nature of the CGM. But I think there are a lot of gaps in our understanding that I'm going to discuss that computer simulations can really play a role in. Now, I know there was discussion earlier that I wasn't present for about how many of the CGM studies by simulations are very problematic, and I generally agree with that. But I think we can potentially get past that. So first off, we're talking about the CGM, so I'm going to try and make this dynamic. So here's our galaxy, and here is a CGM. So we've got our circumgalactic medium, and like the real CGM, it's really hard to see an emission. But we have a variety of different questions that we'd like to be able to answer associated with this. What's it? Yes, I hope there are no chalk allergies. Sorry. What's the extent of it? Does it extend all the way to the virial radius? What's the density profile? What's its shape? Is it spherically symmetric? Is it triaxial? Is it amorphous? What's the covering fraction of it? Is it mostly a monolithic structure, or is it made up of lots of individual absorbers that are sub-parsec in scale? Who knows? What is it dynamic? Is it static? You're feeding it from cosmological filaments, you're feeding it from the inside, so presumably it's dynamic on relatively short timescales because star formation is a relatively short timescale relative to the overall galaxy's evolution. These are a variety of questions that we don't really have answers for, and I'm going to argue that simulations can help us at least at some level. The problem with just straight up observations is that we have to rely, because it's not visible in emission, we have to rely on being able to see it in absorption. So let's see if this works. I need a green laser pointer to pick up the chalk in the air, but we have to rely on background quasars to travel through our CGM to be observed, have the CGM observed in absorption. Yeah. Oh, maybe it'll pick up. Oh, wait, where's? Oh, goodness. It's like a light show here. Well, anyway, so we have to rely on that. And due to the low numbers of quasars in background, you only ever really probe a single galaxy once with a background quasar. So it's not like we can study the nature of this until we're able to observe this in emission, like some of the work done by Sebastiano and some other groups out there that have been able to do this for quasars and the circumquasar medium. We really need to be able to do that to investigate the nature of the spatial extent of the circumgalactic medium in a single galaxy. But for now, we have to rely on these surveys that probe several different ensembles of systems and give you something like this. This is work by Chuck Steidel, where you get, you assume, you have to assume a bunch of things. You assume that all galaxies of a particular type are the same. You have to assume that they're spherically symmetric, and that the only thing that matters is the impact parameter. And so you get a rest equivalent width, or if you do some Voigt profile analysis on it, you get a column density associated with a particular line. In this case, it's carbon lines and silicon lines. And then you get the impact parameter to that galaxy, the radius at which, the projected radius at which this sight line occurs. And this can tell you a lot because these different absorption lines are tied to the different phases of the gas, right? More highly ionized lines are going to be, well, it's all a feature of the temperature, the density, the metallicity, and the radiation field of the gas at that particular location. So, okay, so how do simulations help? This is a slice through a simulation that I did as part of a study last year, and you can see the slice. This is just the gas number density that we're looking at in this slice, and you can see, you may be able to see the velocity profile on top that's overlaid. So because we know, in the simulation, we know the density, we know the temperature, we know all of these quantities associated with the phase, we can throw that into a cloudy table and assume collisional equilibrium, collisional ionization equilibrium, and photoionization, and it'll spit out what the density is associated with any particular ion that we care to look at. So we do this. In this case, we're just going to look at silicon-2 for the purposes of this demonstration. Send a sight line through it at any particular orientation, and we get out what the density is along that line of sight. We also get out what the velocity is for that particular line of sight, and we weight the velocity profile by the density profile, and it gives us out a nice little spectrum associated with silicon-2, this particular one at rest wavelength of 1260 angstroms. And then we can perturb that with signal to noise, with the line spread function of whatever detector we care to look at. In this case, it's the cost line spread function, and get a channel map here. And we can also perturb it with a Milky Way foreground and get out a spectrum that looks somewhat like a spectrum that you get when you actually observe this object. I mention this because YT, which is a simulation analysis routine, that's the main analysis routine used by the Agora consortium. I'm one of the core developers. We just had a major release last week. And for some of the codes, you can do this. There's a HST proposal led by Molly Peebles that I'm involved with that is enabling this to work with all of the codes supported by YT. So if you haven't checked out YT, the new version supports basically all the particle-based codes, all the grid-based codes. There's a lot of really cool stuff, including this sort of analysis that you can do. Okay, so all of that for that single sight line is just going to give us 1 point in our column density versus radius map. And of course, we take lots of different sight lines in our simulation, and it produces something like this. The observational sample here, the points, and the gray arrows representing limits is simply from the COS Halos survey for silicon-2. And then, these lines represent data from tens of thousands of sight lines that I've taken through my simulation data, because I can take as many sight lines as I want to. The individual lines are just the medians of the distribution of points for a particular halo, and the extent here is just the quartiles to give you some idea of the span of the thing around this particular line. Each of these 3 lines represents a different feedback model used for the exact same initial conditions in a simulation. I don't really want to get into the details of this. I've presented it before, but just for feedback, for a few different lines, in a paper that I published last year, some of the lines you do a better job of matching the observational data, some of the lines you do a poorer job of matching the observational data. But again, this is not really the focus of this talk. Oh yeah, so synthetic spectra can be used to directly compare simulations against CGM observations. And in this case, we see that the different lines, which represent different feedback models, do make different predictions for the overall distribution of the CGM. So you can really use that to break the degeneracy in different feedback models. Okay, but the title of my talk today is talking about pressure support and the metallicity bimodality in the CGM. So let's get to that. Okay. Earlier this year, there was a paper that Jess Work put out with a variety of people. X is in the audience, who's a second author on the paper, looking at the nature of the cold absorbers in the COS halo sample. So essentially,
she talked about that here.
Oh, she did? Oh, then I don't even need to yap about it. So. Okay, well, essentially, I'll keep it quick since she already discussed it. Looking at the nature of the cold absorbers and found, did she talk about the pressure support and that it sits super low? Okay, great. Well, then I can go straight to this. So the team looks at the absorber sample and finds that it's very close to the Mahler and Bullock locus for their analytic model for this two-phase, multi-phase model of cold gas and hot gas and pressure equilibrium. And so what I did is used one of my previous simulations and looked at what does the simulation tell us about this. So this is the same plot we were just looking at, but on slightly different colors and such. The analytic cold gas and the analytic hot gas is the Mahler and Bullock 04 model, and those are the locuses associated with that. And here are the observed data from the COS halo sample. And if you look at the simulated data from one of my CGM zoom-in simulations using ENSO, we find that the simulated cold gas absorbers pretty much lies on top of what the analytic model predicts. And it's the same with the hot gas as well. I mean, there's a little bit of a deviation here, but for the most part, it's falling on what the analytic model predicts. And if you assume an ideal gas law and then calculate what the equivalent pressure is for all of these components, obviously we know that the analytic model is in pressure equilibrium because that's one of the parts of that theory. But the simulation is as well where the cold gas and the hot gas are co-located. They're in pressure equilibrium, and they're very, very, very far, two orders of magnitude away from where the observational sample is, which is interesting that simulations, I don't know, I think it's pretty interesting that the simulations are reproducing a very, very, very simplistic model, not to play down R.A. Mahler and James Bullock's work, but it's a simple model, and there's a lot that goes into these simulations, and yet the simulations seem to align with the model.
Yeah, I think the model was really based on equilibrium profile, so it's taking the wisdom from the simulation.
So maybe it's just looping.
But the key point, as you said, is the observations don't agree.
They don't agree at all. Yeah. So
they're cold clouds.
They're cold clouds, and so
Pressure equilibrium.
well, okay. So things that. Explanations for what's going awry here. Okay, so of course, there could be something wrong in the analysis of the observational data, but there are a bunch of other things, even if that observational data has been analyzed properly, it could be that the cold and hot gas are not in pressure equilibrium. These are transient features, like cold gas comes in clumps and then immediately dissolves, and it's just constantly being repopulated in the CGM. You could have them not, the hot and the cold gas, in different regions, so they aren't necessarily in pressure equilibrium because they're in different parts of the galactic halo. You could have them in pressure equilibrium, but there's essentially no hot halo whatsoever. So if we look back at this, it would be as though this simulated hot gas is just way down here. And so that the cold gas drops as well and sits on top of the absorbers. And then finally, there could be some additional pressure support, like magnetic fields or turbulence. So this is something that I'm looking at in an HST theory proposal that's happening this year. So hopefully have some resolution of this, but essentially looking at increasing the resolution in the halo to try and better resolve the individual structure of the CGM absorbers to see if that makes a difference. Okay, and then very quickly, talking about the metallicity bimodality, there was work by Nicolas Lehner last year looking at Lyman limit systems that were only chosen based on their neutral hydrogen content, not based on their metallicity. And what he found was there are two separate populations. One high metallicity component that's about 50% solar, and then one low metallicity component that's about 2.5% solar. And the obvious interpretation given by the group was, there are two main sources of gas into the CGM. There's primordial filamentary inflow, which would populate the low metallicity component, and then there's an enriched component coming from supernovae feedback and AGN feedback that could potentially be responsible for the high metallicity component. So what I did is I essentially looked at this in my simulations. I took the galaxy and I identified sightlines just from a projection, column density sightlines that were neutral, that were Lyman limit systems. So essentially, the two black lines give the two limits on Lyman limit systems, and so this greenish yellowish region is what was identified as a Lyman limit system. And then I overplot that on the metallicity and identify what the metallicity component is of all of these individual sightlines from a bunch of different projections of the galaxy. And essentially what it reveals is similarly you get this bimodal distribution of your metals. But what's interesting, if you look at the relative velocity relative to the center of the galaxy for each of these sightlines, if it's inflowing, if it's outflowing, you find that the high metallicity component is in fact outflowing, which is consistent with potentially this being due to an enriched component that's being blown out by supernovae and such. But this is pretty early work, and again, we're trying to relook at this when we have more resolution, because what you'll notice is the peaks of these are represented as dashed lines, and they're not, the simulated data peaks do not sit on those dashed lines. And so essentially what we took that to mean is if you have insufficient spatial resolution in your halo, you're going to artificially mix like a really, really low metallicity component with a really high metallicity component into a kind of moderate metallicity. And essentially it's going to force each of these peaks inward towards the mean and give you, spurious results. So the hope is that by increasing the resolution, the spatial resolution in our simulation in the halo, it will allow us to distinguish between these two, a pristine component and a really heavily enriched component. And so conclusions are essentially what I've already mentioned. We can use synthetic spectra to compare directly between observations of the CGM and simulations. Different feedback models predict different CGM distributions, and then we can't reproduce the observations of the CGM cold absorbers associated with the Jess work result, but we can seemingly reproduce the metallicity bimodality of Lyman limit systems consistent with Nicolas Lainer's work. So, thank you.
Questions? So what was the resolution that you obtained at
So the resolution of the simulation it gets about 400 parsecs spatial resolution, but that's primarily in the galaxy, because something I was actually talking with Oscar about earlier is in a lot of these simulations, at least in AMR simulations, you have a criterion for increasing resolution. That's usually density. And you get plenty of density and plenty of resolution within the galaxy itself, but the CGM doesn't have a lot of density there. So you have to come up with some additional way of triggering refinement. If I look at the spatial resolution in the halo, maybe 100, 150, 200 kiloparsecs out, it's like 4 kpc, or it's not very good. And so I think that may be responsible for a lot of the problems that at least that I'm seeing, but I think that the field as a whole is seeing, is we just have insufficient spatial resolution in the overall halo. Half kiloparsec. And why? So, but this is with the ART code, yes? So, what are you just using a density refinement criterion, or? Yeah.
But your final, your finest grid cell is 25 parsec.
Oh, right. So it's a factor of 10. Yeah. Okay. Mm-hmm.
So have you looked at the metallicity distribution in your run? You can find it out. No, you can clearly see that the inflow usually has much lower metallicity than the outflow.
Right. Do you see the, what?
Do you see the Metallicity Bimodality evolving this time, or
It appears to be, so I took that snapshot, and there are definitely other snapshots that follow that profile, but there are some where it's just a mess, where it's a single profile, and so it's not like, ding, this is the winner. You know, it's changing a lot, and that's why I have to do some more analysis and run some more simulations to see if I can get some sort of consistent result instead of it just going all over the place. Have you looked at that at all, CG?
yeah, I saw it evolve this time, basically.
Yeah,
It's actually quite expensive to say that Bimodality actually happens.
right,
Really depends on feedback.
on feedback. Oh, yeah. Oh, this? Oh, this.
So it looks like the leaf hydrogen is self-shielded in the regions.
In which one?
In the top one, it looks like there's some kind of self-shielding going on.
It looks like that. You mean because it's so steep?
Yeah, is there indeed some?
There's no self-shielding in these. I know, it looks that way, but essentially what we find is that the lower ionization potential of the ion, the more it has this very peaked and then a very steep drop-off, whereas this is an increasing ionization potential. And then as you increase its, well, here, let me show you. I included a couple of extra slides, just in case. So then as you go to different ions, that steep drop kind of extends outward and outward farther and outward farther until for the very high ionization potential ions, it extends. It's much more kind of a bath of hot gas as opposed to that very peaked. And again, that may be related to the lack of spatial resolution in the outer parts of the simulation. I'm not entirely sure, but it appears to be something that as you monotonically increase the ionization potential, you see more of this kind of extended structure. Yes, it should be there.
Can we get the next speaker to sit up and then can one final?
Since this is a world joint thing, I was wondering if anybody's really planning or leading their efforts to do this kind of comparison for a Bohr simulation.
That's a good question for Joel.
Initially there was some discussion about performance quiz and social line comparisons, but I haven't heard since then what's the effort on that direction.
We certainly need one. I think there's a working group that's supposed to be the circumgalactic medium. Let's discuss it tomorrow.
Yes.
I think Miguel Canal is interested. Miguel Canal is interested in that.
Yeah.
Yeah.
Yeah, let's chat more about that tomorrow. Let's thank Cameron again.
So I'm Cameron Hummels. I'm a postdoc at University of Arizona. I've listed some of my collaborators on this project and some of the other projects I'm going to talk about here, and talking about mostly the circumgalactic medium. So investigating the circumgalactic medium is crucial for understanding a variety of topics that we've been discussing over the week. Things like galaxy evolution, galactic gas accretion, supernovae feedback, AGN feedback, all of these things tie back into the circumgalactic medium, which can be used as a probe, a direct probe, I'll argue, for a variety of these things. For all galaxies' evolution. These are a variety of questions that we don't really have answers for, and I'm going to argue that simulations can help us, at least at some level. The problem with just straight up observations is that we have to rely, because it's not visible in emission, we have to rely on being able to see it in absorption. So let's see if this works. I need a green laser pointer to pick up the chalk in the air, but we have to rely on background quasars to travel through our CGM to be observed, have the CGM observed in absorption. Yeah. Oh, maybe it'll pick up. Oh, wait, where's? Oh, goodness. It's like a light show here. Well, anyway, different questions that we'd like to be able to answer associated with this. What's it? Yes, I hope there are no chalk allergies. Sorry. What's the extent of it? Does it extend all the way to the virial radius? What's the density profile? What's its shape? Is it spherically symmetric? Is it triaxial? Is it amorphous? What's the covering fraction of it? Is it mostly a monolithic structure, or is it made up of lots of individual absorbers that are sub-parsec in scale? Who knows? Is it dynamic? Is it static? You're feeding it from cosmological filaments, you're feeding it from the inside, so presumably it's dynamic on relatively short timescales because star formation is a relatively short timescale relative to the overall. And really, the CGM, we understand a lot about it from observations, but it operates in this unique space because it's the interface between the tenuous IGM and the star-forming ISM, and so you have a lot of different mechanisms going on there. You have stars forming and dumping, depositing metals, energy, and such into the CGM. And then you also have cold filaments and primordial gas flowing into and shocking in this region. So there's a lot going on. Observations have been in the last 10 years have really taken off, especially with the cosmic origin spectrograph aboard HST, enabling a variety of different observational studies like the COS halos to exist and to really touch on the nature of the CGM. But I think there are a lot of gaps in our understanding that I'm going to discuss that computer simulations can really play a role in. Now, I know there was discussion earlier that I wasn't present for about how many of the CGM studies by simulations are very problematic, and I generally agree with that. But I think we can potentially get past that. So first off, we're talking about the CGM, so I'm going to try and make this dynamic. So here's our galaxy, and here is a CGM. So we've got our circumgalactic medium, and like the real CGM, it's really hard to see an emission. But we have a variety of different